Logistic regression is a powerful machine learning technique used for classification. It helps us predict probabilities for a given input, which in turn allows us to decide between categories. For example, is the answer yes or no? Will it happen or not? The foundation of logistic regression lies in the sigmoid function, a mathematical tool that converts any number into a probability between 0 and 1. Let's think of it as a guessing game. Suppose you want to answer questions like, will it rain tomorrow? Is this email spam? Or, is this fruit an apple? These are all examples of yes or no questions where logistic regression can help. Now, let's visualize how logistic regression works. Imagine it provides a probability for each possible outcome. For instance, here's a scenario about predicting rain tomorrow. The probability that it rains might be 0.75, and the probability that it doesn't rain might be 0.3. What does this mean? Logistic regression uses a simple rule to decide. If the probability of yes is greater than or equal to 0.5, we predict yes. Otherwise, we predict no. In this case, since 0.75 is greater than 0.5, we predict yes. It will rain tomorrow. On the other hand, 0.3 is less than 0.5, so we predict no. It will not rain. In summary, logistic regression doesn't just give you probabilities. It helps you make decisions. By using the threshold of 0.5, it predicts whether something belongs to one category or the other. It's like saying, if I'm at least 50% sure, I'll say yes. Otherwise, I'll say no. So, to put it all together, logistic regression predicts outcomes based on data and probabilities. If the probability is greater than or equal to 0.5, the answer is yes. Otherwise, it's no. Simple, yet incredibly useful for solving real-world problems. The foundation of logistic regression lies in the sigmoid function. It's a mathematical tool that transforms any input value into a number between 0 and 1, making it ideal for modeling probabilities. Let's start with the equation for the sigmoid function. It's expressed as 1 divided by 1 plus a raised to the power of negative x. This equation might look complex, but its beauty lies in how it converts numbers into probabilities. Now let's visualize the sigmoid curve. This curve has an elegant S shape. The higher the input value, the closer the output moves to 1. On the other hand, if the input value is smaller, the output approaches 0. This makes the sigmoid function perfect for classification tasks where the goal is to predict probabilities between yes and no. Notice how the sigmoid function compresses extreme input values into probabilities near 0 or 1, while mid-range values are mapped to probabilities between these extremes. This property ensures that logistic regression can handle a wide range of inputs and still provide meaningful probabilities. In summary, the sigmoid function is the engine behind logistic regression. It transforms raw inputs into probabilities that help the model make decisions. The S-shaped curve is what gives logistic regression its ability to classify data effectively. The sigmoid function is a smooth, S-shaped curve widely used in machine learning, particularly in binary classification and neural networks. The sigmoid function is mathematically defined as sigma of x equals 1 divided by 1 plus a raised to the power of negative x. Let's dissect the components of this formula to understand its behavior. The co-component of the sigmoid function is a raised to the power of negative x. This term creates the characteristic curve of the sigmoid function. Let's explore the behavior of a raised to the power of negative x for positive x values. When x is a large positive number, negative x becomes a large negative number, and a raised to a large negative number approaches 0. When x is a large negative number, negative x becomes a large positive number, and a raised to a large positive number becomes a very large number. Adding 1 to the exponential term ensures that the denominator is always greater than 0, preventing undefined behavior from division by 0. Dividing 1 by the denominator ensures the output is always between 0 and 1, which is why the sigmoid function is commonly used to represent probabilities. Now, let's visualize the sigmoid curve. The sigmoid function maps input values to a range between 0 and 1. As you can see, the curve transitions smoothly from 0 to 1, with a steep change near x equals 0. For large positive inputs, the sigmoid function approaches 1. For large negative inputs, the sigmoid function approaches 0. At x equals 0, the sigmoid function is exactly 0.5, dividing the curve symmetrically. The curve has horizontal asymptotes at y equals 0 and y equals 1. While standard logistic regression is designed for binary classification, it can be extended to handle multi-class classification problems in several ways. Multinomial logistic regression is a direct extension of logistic regression. It models the probability of each category separately and assumes no order among the categories, such as predicting types of fruits like apples, bananas, or oranges. 1 versus rest, or 1 versus all, is another technique. Here, we train a separate binary logistic regression model for each class. For each model, we treat one class as positive and all other classes as negative. To make a prediction, we choose the class with the highest probability. Ordinal logistic regression is used when the dependent variable has more than 2 categories, and there is a natural order among the categories. For example, predicting movie ratings like 1 star, 2 stars, or 5 stars. To summarize, logistic regression can be extended in 3 ways. Multinomial logistic regression for multi-class problems with no order. 1 vs rest for separate binary models. And ordinal logistic regression for ordered categories. Logistic regression is widely used in various fields. Its ability to provide probabilistic outputs makes it a powerful and interpretable classification tool in machine learning. One of the most common applications of logistic regression is spam email detection. Here, logistic regression classifies emails as either spam or not spam, based on features such as word frequency and sender information. Logistic regression is also used in disease diagnosis. For example, it can predict whether a patient has a disease based on clinical parameters such as blood pressure, cholesterol levels, and age. Another key application is predicting customer churn in businesses. Logistic regression analyzes customer behavior and predicts whether a customer will stop using a service based on factors such as usage patterns and customer support interactions. Logistic regression is also used in marketing to predict the success of campaigns. It evaluates customer data to determine whether a customer is likely to respond to a marketing offer, helping businesses target their audience effectively. Logistic regression is best suited for binary classification problems, when the target variable is categorical, and when probabilistic interpretation is required. Logistic regression excels in binary classification tasks, such as predicting spam emails or loan approvals. It is suitable when the target variable is categorical, like whether a person has a disease or not. Logistic regression is ideal when you need probabilistic outputs, such as the likelihood of a customer making a purchase. Logistic regression provides interpretable results, making it easier to understand the relationship between features and predictions. However, logistic regression is not ideal for multi-class problems without modification, nonlinear relationships, or large datasets with complex patterns that require more powerful models. Logistic regression struggles with multi-class problems unless extended with techniques like 1vs rest or multinomial logistic regression. It is unsuitable for nonlinear relationships, where features in the target variable don't follow a linear pattern. Logistic regression may not perform well on complex datasets with high-dimensional data, like images or text embeddings. Logistic regression is inefficient for large-scale data with millions of records, where advanced models like neural networks or gradient boosting might be more appropriate. Logistic regression is a powerful statistical method used to predict the probability of a binary outcome. Let's summarize its key concepts and applications. Let's explore these points one by one. Logistic regression is widely used for binary classification tasks, such as determining whether an email is spam or not. It predicts the probability of categorical outcomes, making it useful for probabilistic interpretations. The output is modeled using the logistic or sigmoid function, which maps predictions to values between 0 and 1. Logistic regression assumes a linear relationship between the input features and the log odds of the outcome. It is optimized using techniques like maximum likelihood estimation, which identifies the best parameters for the model. Model performance is evaluated using metrics like accuracy, precision, recall, and ROCAUC, which assess its predictive capabilities. Logistic regression works well when features are independent and the data is linearly separable. However, it struggles with nonlinear relationships unless additional feature engineering or extensions like polynomial features are applied. Finally, logistic regression has diverse applications, including medical diagnosis, fraud detection, and marketing predictions. Mastering logistic regression helps you build strong predictive models for binary classification tasks. Remember to check for linear separability, validate assumptions, and interpret model coefficients carefully for actionable insights. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up. Subscribe to the channel Leave a comment and share it with your friends. Your support means a lot. See you in the next video.